today we're going to learn about using applied math to model Ebola. So what we're going to do is we're going to look at the Ebola virus, learn a little bit about it, learn about its biology, and then we're going to see how math can be used to prevent the virus from spreading and preventing an epidemic. So just a little overview, we're going to look at why we're interested in Ebola in the first place, and then we're going to learn all about the virus and about the outbreak in West Africa, which is where we'll be focusing our model. Then we'll take a break into the math portion of this, and we'll learn about ordinary differential equations, and then we'll move on to making our model. So why are we interested in Ebola? Well, in 2015, there was a huge outbreak. I'm sure a lot of you remember hearing on the news. Ebola was a big deal, and a lot of people were getting sick. So as of 2015, there were about 22,000 cases that were just reported. So that's kind of a guess from the World Health Organization data, or the WHO. I'll reference them a lot during this talk because that's where I got my data from. But those are just the reported cases. There's many other cases that probably go unreported in these rural areas. And then of these 22,000 cases, 9,000 of them resulted in death. So it's a pretty deadly virus. If you catch it, you have about a 50% chance of surviving. So this outbreak in 2015 in West Africa was the worst outbreak in humans that anyone had ever seen with this virus. And so currently, Ebola is still prevalent in Western Africa. It's a little less heavy, but it's still there. People are still catching it and still dying from it. There's about a little over 28,000 cases now that are reported, and a little over 11,000 deaths. And now, with the spread of the virus, we're in a modern era. People travel, people get on planes, they don't really realize they're sick yet. So now it has spread to 3 continents, Africa, North America, and Europe. So we're really interested in stopping the spread of this virus and trying to figure out how we can predict its course and where it's going in order to stop it. So I have a little clip for you guys.
When a disease is this contagious, even cautious medical professionals are at serious risk. The virus spreads through contact with bodily fluids and is fatal in up to 90% of cases. 2 Americans working at treatment centres in Liberia have been infected, one of them 33-year-old Dr. Carl Brantley, seen here on the left. The World Health Organization has told the BBC that in total, around 100 health workers in West Africa have been infected this year. Half of them have died. This is the deadliest outbreak of Ebola on record. The latest figures from the World Health Organization show more than 1,200 people have been infected in Guinea, Sierra Leone and Liberia, and around 670 of them have died. More than 300 of those deaths were in Guinea, more than 200 in Sierra Leone, and more than 100 in Liberia. And now, the first death on Nigerian soil. A Liberian man died after flying from Monrovia to Lagos. That case highlighting how difficult it is to prevent infected people from travelling. Screening systems in West Africa are weak, and the initial symptoms of the disease, including fever and a sore throat, resemble many other illnesses. So Liberia has now closed most of its border crossings and set up testing centres at the few major entry points which remain open, including its international airport. In Nigeria, all points of entry, air, sea and land, have been placed on red alert, trying to halt the further spread of one of the world's most virulent diseases, which has no vaccine and no cure. Emily Thomas, BBC News.
Okay, so what we learned from that video is that this disease is targeting a very rural place, West Africa, and there's not much systematic preventative measures put in place to stop the spread of the disease. So one thing we really want to focus on is kind of charting the course of the virus and seeing how it's spreading and who's getting it and how fast it's being contracted and being spread. That way we can kind of curb the spread of it and among people and territorially as well. Okay, so symptoms of the Ebola virus. There's fever and chills, headache, muscle pain and weakness, internal bleeding, and at the later stages, you're vomiting or coughing up blood. You have multiple organ failure. And once you do show these symptoms, there's about a 50% chance that you will die from this virus. And so once a person becomes infected with the virus, they can die in as little as 2 days, or they're ill for up to 21 days. And that's because once you're come into contact with the virus, there's an 11-day incubation period. And what an incubation period is basically the virus is multiplying within you, and you're not showing symptoms yet. So you might have no idea that you're sick for up to 11 days when you actually are sick. And then after that 11-day period, you'll start showing symptoms, you'll become very contagious, and then you can die within up to 10 more days. So there's no vaccines to prevent or to cure the disease or prevent it from being contracted within a person, but you can treat the symptoms of Ebola. So with that, you can hydrate yourself, take fever reducers, inject antibodies from previous survivors. Basically, if you have access to good healthcare, you have a higher chance of survival. But in these West Africa rural areas, there are limited options to healthcare. So the current situation is bad. It's now spread to 2 other continents, so it's on 3 continents total, and we want to stop this from becoming an epidemic. So we're going to use math to chart our course out and map a solution to preventing an epidemic. So to do that, we'll use ordinary differential equations. So a differential equation is a mathematical equation that relates to some function with its derivatives. So basically, a derivative measures the change over time. So we all know like y equals mx plus b. M is the slope, and that's the change over time. And so what differential equations do is they use these rates of change as variables. So we're going to kind of be mapping the course of the virus over time. So this is our tool for predicting the virus's moves, and this will help us model how the virus goes through the population over time. Okay, so now that we know a little bit about the virus, we can kind of break it up into stages. So everyone starts out as susceptible. We're all fine, we're all healthy, no one has Ebola, we're susceptible to catching it. And then you have people who are in the incubation period who have been exposed to the virus. They're now not showing symptoms, but they do have the virus in them. And then third, we move on to the infectious period. This is when you've gone through your incubation phase, you're now showing symptoms, you can pass the virus on to other people, and you're infectious. And then from there, after you're infected and you're showing symptoms, you either recover from the disease or you die. And so we have recovery or death. You can move to one or the other. So now we're going to break this out into phases. So here's a diagram that we'll kind of be basing our model on. So basically, everyone starts out susceptible to the disease. You can catch it, but you're fine, you don't have Ebola yet. But if you come into contact with someone who is infected with Ebola, you will contract the disease. So from there, you move into the E phase for incubation period, because we already used I for infected. So E for incubation. And so from there, you'll sit there for 11 days. And then after 11 days, everyone will move on to the infected phase. And then once you're infected, after 10 days, you'll either move on to recovery or to death. So that's kind of how we map out the flow of this disease. And so then we have to take into consideration some assumptions, as with any model. So we're going to assume that we're looking at the area of Western Africa. We're going to assume that there's a fixed population. So no one's coming in on planes, no one new is being born, that kind of thing. We want to look at a fixed set of people. And then we're also going to assume that no one is immune to the virus. So no one's naturally immune, no one naturally has antibodies that could prevent them from becoming infected. So what that means is if you're exposed to someone that's infected with the virus, you're going to catch it. And then the only cause of death is from Ebola in this instance. You're not moving into the death group, the D group on here, unless you're dying from Ebola. And then we're going to assume that the initial number of people that are susceptible, so basically almost the entire population, is 6.9 million. So we're going to have this group of 6.9 million people that are free of Ebola and see what happens to them. And then we're also going to assume that the initial number of people in incubation is 25. We have to assume that some people are in the incubation and infectious phases, or else no one would catch the virus, because no one has it to begin with. So we assume 25 people are in incubation and 50 people already have the virus and are showing symptoms. And then we're going to assume that the initial recovered population is 0 and the initial death population is also 0. We're also going to assume that once a person moves to the recovered group, that they remain there. So you're not going to go through the course of the virus and then catch Ebola again once you're clear. And then also, if someone moves to the deceased group, then they stay deceased. Pretty fair to assume. And then we're also going to assume that the incubation period of the virus is 11 days. And then, like I said earlier, the time it takes to move from being infected to either recovery or death is 10 days. So a total 21-day course of the virus. Okay, so now we're going to start making our equations. So for our susceptible equation, we want to think about who is moving from the susceptible group into the incubation group. So what is leaving susceptible and going into incubation? And it's the people contracting the virus. So what we kind of think of this as is we have our total number of people in S, and then we have our total number of people in I, so susceptible people and infected people. And then there's some kind of infection rate between the two that'll make the move of people from S to incubation. And then the same is true. So I used 2 infection rates. So alpha represents the infection rate from people who are in the I category. So the people that have Ebola and are infected, they have a certain rate of passing it on to someone else who comes into contact with them. But then also in Western Africa, a lot of people were actually contracting the virus based on burial practices. So they weren't actually catching the virus from people that were alive, they were catching the virus from people who died. And so I wanted to make sure that our model took that into account because that's how the majority of people were actually contracting the virus. So we have 2 separate infection rates, alpha and beta. And so alpha will represent the infection rate of infected people, and beta will represent the infection rate of deceased people. So people who have already died from Ebola. And so both of these equations are negative signs because they're leaving S. So this is our S equation, and people are leaving S based on the number of infected people and the number of dead people. And then for our incubation equation, we want to think about who's coming into the incubation period and who's coming out. So the people that are coming in are the people from the susceptible equation, right? The people who got the virus and now they're waiting in the incubation period to start showing symptoms. So this is exactly what was in our first equation coming out. So that's what's going to be coming into the next equation. And then what's coming out of this incubation period equation is the people coming in times a delay factor of 11 days. So all the people that are contracting the virus are coming into the incubation period, they're staying there for 11 days, and then they're all coming out. And so what this represents is, this part is our equation from the susceptible population. So alpha times the infection, or the people that are infected, and then beta times the people that are dead. So that's positive because it's coming in. And then right here is the exact same thing, but we just multiplied S times T minus 11, so time. This is the time delay of 11 days. And then again, 11 days. And then here is the beta SD with the 11-day incubation period. So we're just looking at a delay of 11 days for people coming in and leaving. And then for the infection phase, the people coming into the infection phase are the people who were leaving incubation. So after 11 days of sitting in the incubation period, you're going to become infected with the virus and start showing symptoms. And then the people who are leaving the incubation phase are either moving on, or the infection phase, sorry, are either moving on to recovery or to death after 10 days. So we have the people coming in from the incubation period after 11 days, and then we have the people coming into the infection phase times the death rate times the delay of 10 days. And then the people that are moving on to the recovery are the people coming into I times the recovery rate times the delay of 10 days. And so what I did for this model was I said that the percentage of people dying would be 60% and the people recovering would be 40%. So we can kind of think of the death rate as 0.6 and the recovery rate as 0.4. So about 60% of the people that are coming into the infection phase are going to move on to the death phase, and 40% of them will move on and recover and not have the virus anymore. So that can be broken out into that long, nasty equation. Okay, and then the recovery population. So the only people moving into the recovery phase are people that were in the infection phase, and we assumed that it was 40% of them. So after 10 days, they're going to move in to the recovery period. And so we can see that time delay right there is 10 days. And then for the deceased population, we have the same thing, but just 60% of them from the infection phase are going to move on to the deceased population. So we see that equation there. Those are all of the equations together, and they work as a system. On this slide, so we have 0.4 total, but we have 40% total, but half of that is from the alpha for our infection rate of the infected people, and then the other half is the beta infection rate from the deceased population. So 0.2 and 0.2 is 0.4, 40% total. And the same is true for this equation. For the death rate, it's 0.3 and 0.3. So the time that it takes once you get into the incubation period, it's 11 days before you get into the infection period. And then once you're here, it's 10 days to move into either deceased or recovered. So you have you're in incubation for 11 days, not really showing symptoms. And then once you're here, you're showing symptoms for 10 days before you move on. If you have treatment of symptoms, like the hydration and taking aspirin or fever reducers and just access to good, clean water and clean health care, yeah, and it'll process through your body. But if you don't, obviously, you're probably going to die from the virus. And so it's pretty accurate. We based all of the rates off of the World Health Organization database. And so at the time in 2015 when we made this model, it was about a 60-40 rate. So about 60% of people getting infected were dying, and about 40% were recovering. And now I think it's moved down a little bit to 50-50. So a little less people are dying, because I think it has to do with medical brigades being sent to Africa, people treating the symptoms and doing everything they can to infected people, helping them try to fight it on their own. For a while, there was a ban on burial practices altogether, and I think the CDC actually took care of it themselves. So you weren't allowed to see your loved ones after they died at all. But now I think since people know how you contract the virus, it's more well known now, and they've been educating those areas. It's less common. They still let them do that. Yeah. So this is the model that we see when there's no vaccination and barely any treatment of symptoms. So let's see what the results of our model were. Okay, so our model shows, we mapped it through a software that ran all of those big equations together over time and kind of did it day by day and showed us who was in each of these groups after however many days we wanted. And so after 47 days, it showed that 792 people died from Ebola, and that there were still almost 3,000 people after just 47 days who had contracted the virus and were in the incubation period. And there were also a little over 1,000 people that were still infectious and still spreading the virus. So you can see out of a population of almost 7 million, already almost 800 people died, and thousands are infected and about to spread the disease. And so this virus doesn't have a very high infection rate. It's kind of hard to contract it because it's contracted through bodily fluids. It's not like it's airborne or anything. But once you have the virus, there's a very high chance that you will die. And so we kind of took a look at this and took a step back and said, well, if it's not very infectious, how can we prevent people from contracting it in the first place? So we thought, what if there was a virus, or a vaccination, sorry. So a vaccine could be administered and prevent you from contracting the virus. So let's say you're next to someone and they have Ebola, but you have the vaccine, then you wouldn't contract the virus from them. It would prevent it from getting to you altogether. So when we were thinking about introducing a vaccine into our model, we had to take some things into consideration, primarily how effective the vaccine would be. And so most vaccines actually range from 95 to 99.9% effective, which is really good. Good news. We want them to be effective. And so for our model, we just assumed, for simplicity, that it would be 100% effective. And then we assumed that it would take 5 days for that vaccine to take effect. So once you're vaccinated, after 5 days, you're immune to getting Ebola. And so for our model, what we did was we said, what if we could administer the vaccine to these big cities? Because remember, this is in rural West Africa. It's hard to get to these small farm villages and these rural cities. There's not good roads, not good transportation. So how are we going to get the vaccine to people? So we decided that if we would tackle some 3 major cities, that's how we would administer the vaccine. So we're going to administer it to everyone in these big cities. And even though that accounts for only 20% of the total population, we think that that'll be a good stop, because that's where this disease is spreading, when people are traveling to the big cities, going to airports, coming from rural villages, and then moving out. So it's kind of like a hub. So that's where we decided to attack it, kind of. And so this impacts our model mathematically, because more people will be moving out of the infected phase more quickly, and more people who have already been infected will be moving to recovered instead of death. Okay, so once we added a vaccine in, we found that this strategy would decrease the number of deaths from Ebola by 96%. That's huge. So it's a 100% effective vaccine, but we assumed that not everyone was getting it, right? It was only 20% of people that were getting it. And so by giving the vaccine to those 20% people in those big cities, it reduces the number of deaths by 96%. That's huge. And so this curbs the outbreak and prevents an epidemic, because people are traveling to the cities and the virus kind of stops there, because it's not going to infect anyone new. And then administering the vaccine to densely populated cities prevents the spread. It doesn't get to the rural areas that way. So the point is that math is really cool. We used math to basically map out the virus, see what it was doing, see how many people it was infecting and how quickly, and kind of make a proactive step to see how could we stop this virus. And so we basically just predicted the future. And organizations like the World Health Organization and the Department of Defense use these kinds of epidemiological models like I just showed you every day. They use them to predict viruses, predict epidemics. I'm sure if you Googled Zika virus epidemiological model right now, you'd find a ton on the internet. People really do use these to come up with vaccines and see if vaccines could cure, or not cure, but help curb an epidemic. And so there's math behind all vaccines and medications. So we just use math to better understand. We can use math to better understand almost anything in this world. We just used it to understand a virus and understand an outbreak and understand how a vaccine could stop an epidemic. So you can really apply math to almost anything. We actually did this research over 5 days for a math modeling competition. And so, I know I sound really cool, math modeling competition. But so we didn't have time for that. But we kind of, for these kinds of models, what's pretty standard is you have a fixed population, just because it's really hard to have people coming in constantly when you're trying to calculate these answers and these equations. So at a certain point in time, it's hard to predict it for an unlimited population. Yeah, that's definitely something that I'm sure the World Health Organization and the Department of Defense are able to do. I think how it works is when people move into the infected phase, they go from the incubation to the infected phase, but then they move to recovered. So they're not actually physically becoming infected with the virus, but the number of days it takes, they kind of technically move there with the model, but they're not actually infected. if that makes sense. We just had to have somewhere to put them after that amount of days. I would probably want to look at the vaccine more and say if we could realistically vaccinate 20 people a day, 100 people a day in each city, how would that affect the model? Yeah. Because I think it's kind of unrealistic to vaccinate 100% in one city. I did another one of these models on yellow fever, and there actually is a vaccine that exists, and it's, I think, 96% effective. So in that model, we did see people that were vaccinated still getting infected with the disease. The yellow fever one that I did was done over a whole semester, and so that one does have the staggering, like, okay, what if we vaccinated 20 people a day? What if we vaccinated 100? What if we treated 50% of the people's symptoms with fever reducers and hydration? And so that one is it takes in more variables and more factors. The vaccine was introduced like 5 or 6 years ago, so people really aren't dying from it anymore, but there are still some cases of it every year, especially in countries where it's spread like to a different continent and the people on that continent haven't gotten the vaccine because it's never been there before. So we do see some of those deaths from that. When we were trying to say like what's the actual infection rate, every like World Health Organization article said people are mostly contracting the virus from burying the dead. And so we were like, is it really fair to base the infection rate solely on the number of people currently infected? Probably not. And so that's how we tried to take into account one cultural aspect. Yeah. Because that's not how you would contract the virus here, probably. So. But in West Africa, that's how most people were getting it. I'm an analyst at MedImpact Healthcare Systems. So basically what I do is I manage benefits like health insurance, and I try to save people money, save customers money, save our clients money, and give them the right access to the right drugs. And I graduated from the University of San Diego with a degree in applied mathematics and finance. I was really interested in accounting and finance and business. And what I found was that my math classes were teaching me so much more that I could relate to every subject that I was learning. So like in this instance, we just used math to figure out biology, to figure out a virus and vaccines. And so what I liked about my math classes was I would be learning a subject in math, and then I'd go on to my next class and be like, hey, I just learned something that applies to this in my math class. And so I really liked how you could really use math as a foundation for everything. And I thought that if I mastered that topic, then I'd be unstoppable. So, all right.
Well, thank you so much.
Yeah, thank you guys.